Hello everyone. Today week's class we have atomic UV visible spectrum and electronic spectroscopy. It involves energy level transition of the electrons surrounding an atom or a molecule. So if you look at this case here, you can see that we have electrons that are arranged in hydrogen-like orbitals, where the well-known Bohr model for nitrogen. Then we have molecules. Electrons are actually now arranged in the HOMO and LUMO, what we call the highest occupied molecular orbital and lowest unoccupied molecular orbital. For example, as we always see in benzene. So UV-Vis spectroscopy, it is a spectroscopy in the optical range involving electronic energy levels excited by electromagnetic radiation. So technique discussed in this class are related to high energy non-optical methods covered in X-ray spectroscopy lecture. The methods will include atomic absorption, atomic emission, atomic fluorescence. So this is just electromagnetic spectrum, as you all know. So the region we are interested in is the ultraviolet and the visible region. As we all know that the range is from, we could talk of 200 to 800. Then elemental analysis, we can do it both qualitative and quantitative, where we can check the elemental composition of a sample. The atomic UV visible spectroscopy methods are heavily used in elemental analysis. Other elemental analysis methods that are not discussed here are mass spectrometry. We have X-ray methods, we have radiochemical, we have classical methods. So these are absorption, radiation, electronic processes, which we call, one of them is absorption. So absorption is radiation selectively absorbed. And remember the word selectively, meaning it is not just a random selection. It is quantized. So these molecules, ions, or atoms absorb specific intensity of light, and then they are excited. The electrons are excited to a more energetic state. Then now when they release that energy, that is what we call emission. So emission is the radiation produced by excited molecules, ions, or atoms as they relax to lower energy levels. So the absorption process, electromagnetic radiation travels fastest in a vacuum. So when electromagnetic radiation travels through a substance, it can be slowed by propagation, or in bracket interactions that do not cause frequency changes, like what we saw with the refraction. There is no change in energy. But whenever we talk of absorption, this means that there is a change in energy, because a particular portion of the electromagnetic radiation has been removed and transferred to the molecule or element. So in that case, when something is absorbed, it means there is a fraction that is not passing. So there is two definitions here. We have what we call transmittance and absorbance. So transmittance could be seen as the incident electromagnetic radiation, and then the resultant, or the initial and the final. So we would rather do concentration versus transmittance, or absorbance versus concentration, as you can see. So for the case of transmittance, we always have a curve, but when we talk of absorbance, we always have a straight line, and that is, as you can see here, I have noted that this one is preferred. It is easier to deal with a straight line. And that brings us to what we call Beer-Lambert's law and quantitative analysis. If, for example, we wanted to know the amount of a substance in a particular sample, it would be easy for us to use Beer-Lambert's law and absorbance. And Beer-Lambert's law can be seen here. A is equal to mole absorptivity. Then we have path length and concentration. So you can see here what we call the mole absorptivity. Then we have the path length of the sample, which is B. Then we have concentration of the compound in solution. And so Beer's law can be derived from a model that considers infinitesimal portions of a block absorbing photons in their cross-section and the integration over the entire block. So what that simply says is, if you look at the path length, you can consider it to have a lot of cross-sections that makes up that particular, we will talk of it as a box. So if we take that the absorption of electromagnetic radiation by the sample is uniform, then to get the amount or the absorbance, we will do integration. So, but of course there is deviation. We know that when our sample is very much concentrated, it starts to deviate from Beer-Lambert's law. So intermolecular interaction at higher concentrations, chemical reactions, species having different spectra, and peak width stroke polychromatic radiation, all those lead to Beer-Lambert's deviation from Beer-Lambert's law. So the Beer's law is only strictly valid with single frequency radiation. So we can be able to see a scenario where there is deviation. As you can be able to see, a higher concentration causes the spectrum to change. So in that case, deviation caused by use of polychromatic light on a spectrum in which mole absorptivity changes a lot over the bandwidth of the light. Consider two wavelengths A and B. with the molar absorptivity A and B. So if you can be able to see here, so that is just like a correction for such a situation where we have polychromatic light. That is how we'll go about it to do a correction for Beer-Lambert. Then atomic emission, two types of emission. There is what we call continuum, and also we have line spectra. So the examples here is the inductively coupled optical emission spectroscopy, also known as ICP-OES. And then we also have laser induced breakdown spectroscopy. The emissions process, atoms or molecules are driven to excited states. So you can be able to see here, we have a lower state here. When it absorbs energy, it goes to higher state, but when it was to go back to lower state, it has to emit this energy, the energy equal to what was absorbed. That is what leads to what we call emission. Other processes can happen instead of emission, such as non-radiative relaxation, where we have transfer of energy by random collision. So that can also happen. So in atomic or elemental UV-Vis, samples used in optical atomic spectroscopy are usually atomized. From the word atom, it means they have to be in their atomic forms. So this destroys molecules if present and leaves just atoms and atomic ions. Of course, that is not a problem, because if our interest is atoms, then we won't lose anything by getting rid of molecules. So you can be able to see the process, where the first process is nebulization, where you introduce the sample into a plasma. So in the plasma, we call the process dissolution, where we are removing the liquid part. And then after removing the liquid part, we move to the vaporization. So in the vaporization is where now we are getting rid of the molecules, as you can be able to see. So then we are left with only atoms, what we call the process atomization. So that leads us to what we call atomic electronic energy levels. And electronic energy levels transition in hydrogen, it is the simplest of all. So we have in the visible region the Balmer series, where the transition start or end with the first excited state of hydrogen. Then we have Lyman series, transition start or end with the ground state of hydrogen. So for Balmer, with the first excited state of hydrogen. Remember excited state. Then for Lyman, for ground state of hydrogen, as you can be able to see. So that leads us to what we call term symbols, because when we are talking of excited state, it means there is transitions. So these transitions are governed by some rules, what we call the term symbols. and electronic states. So used it precisely to define the state of electrons. So those are some of the terms that you see here. This is the what we call spin multiplicity, as you can be able to see. So the S in the formula there stand for total spin quantum number. The J here stand for total angular momentum quantum number. Then we have orbital quantum number, which is this one here. Then we have MJ here, is the state. So those ones can be well understood if a lecture is done specifically for that. So the term symbols, we know that the quantum numbers are N, L, M, and MS. So N talks of electronic energy levels, 1, 2, 3, 4, as you continue. Then we have the L, where we can start with 0, and then we have 1, 2, 3, up to n minus 1, and that is done with the S, P, D, F orbitals. Then we have ML, and that's ML, we can start with the L, then L minus 1, then as you can L minus 2, continue like that, 0, then we start now to the negative, and that way, as you can be able to see. That's explained there. Then we have MS, which is either positive a half or negative a half. So more explanation: angular momenta associate with the orbital and spin motions in many electron atoms. The interaction can occur of three types. There is the spin-spin coupling, there is orbit-orbit coupling, then there is spin-orbit coupling. There are two principal coupling schemes used. So we have the Russell standards, we have the JJ coupling. So for the Russell standards coupling, you can be able to see those terms that we are talking about: the S, the L, the J, the S, and the MS. So you can be able to see in this scenario, can be able to see a total orbital momentum. So you can be able to see how this works. You can be able to see how this works. The ground state to excited state, selection rules. And you can be able to see change in N is not equal to 0. Change in L is equal to plus or minus 1. Change in S is 0. Multiplicity remain the same. Change in J can be 0 or plus or minus 1. For transition metals, transition between states of the same parity are forbidden, what we call the Laporte selection rule. Like for example, G to G transition forbidden, G to U transition allowed. Then change in S is equal to 0, multiplicity remain the same. For example, as you can be able to see, multiplicity remains the same. Spin allowed, and you can be able to see this one is forbidden because the multiplicity is different. So those are what we are talking about here. So you can look at energy levels for different atoms. So for example, the unknown, because we always compare with the library. So let's say we have unknown and we have the library. So if you can see well, if you compare unknown and you look at the spectrum for strontium, you can be able to say that the unknown is strontium. So atomic electronic energy levels, term diagram for the sodium atom, as you can be able to see. Each transition on the diagram can be linked to a peak in the UV-Vis spectrum. The number of lines can approach 5,000 for transition metal elements. Then line broadening can be caused by the Doppler effect, pressure broadening, and lifetime of state, which is uncertain. So the basic instrument designed for atomic UV visible spectrometer, you can be able to see here atomic the source of radiation source. Then we have a sample in a torch. It goes through a sample in a torch. Then the wavelength selector, and then the detector. For emission, we don't have to do any absorption. The source and sample in a torch, then wavelength selector, and then the detector. So wavelength selector is mono or polychromator. Sources for atomic emission. You can be able to see the flame, which is the temperature is not very high compared to plasma, which is having a lot high energy source. Then we have electric arc, then we have electric spark. Majorly we use the plasma. Yeah. Then we have, you can be able to still see an argon ICP torch in action, how atomization is done. Very hot, 4,000 to 8,000 kelvins. That is just another view of argon inductively coupled plasma torch. Arc and spark sources. So we have majorly used for qualitative analysis of organic and geological samples, only semi-quantitative because of source instability. Spark sources achieve higher energies several milligram of solid sample is packed between electrodes, 1 to 30 Armstrongs of amperes of current is passed, achieving several hundred of volts potential. Application include metal analysis or cases where solid must be analyzed. So the monochromators, you can see the design. Those are the design for monochromators. Then also you can be able to see how light is being separated. So high sample through rate for polychromators. Spectral interference can be an issue if the interfering spectral line is not included on the detector array. But for monochromators, flexibility to access any wavelength within the dimensions of the monochromator. Good for application requiring complex background correction and less sensitive, lower radiation throughput. They are less sensitive. So atomic emission, diffraction gratings. So gratings generally are used to reflect or disperse light or wavelengths, like the KL gratings are known for high dispersion and high resolution. So you can be able to see the gratings there. Then detectors in atomic UV-Vis. We have the PMT, the photomultiplier tubes, and the dynamic range is 10 raised to power 9. Solid state detectors, where we have the CCD, charge coupled devices. Then we have also silicon photodiodes, and then we have 2D. These detectors are very sensitive, very well suited to 2D equilibrating polychromators, very fast. So majorly are just the PMT and the CCD and silicon photodiodes. Then photomultiplier tubes, maybe you worked with it. It's a vacuum tube that contains a photosensitive material called the photocathode. So the photocathode ejects electron when it is struck by light. These ejected electrons are accelerated towards a dynode, which ejects 2 or 5 secondary electrons for every electron that strikes its surface. The secondary electrons strike another dynode, ejecting more electrons which strike yet another dynode, and so on. What we call the electron multiplication. So the electrical current measured at the anode is then used as a relative measure of the intensity of the radiation reaching the photomultiplier tubes. So the modern ICP optical emission spectroscopy, can be able to see the example there of the spectrometers. You can be able to see. So detection limits. As you can be able to see there, typical detection limits consideration include the number of emission lines, spectral overlap. So, and then linearity can span several orders of magnitude. You can be able to see. Then you can be able to see that atomic emission was the only way to do elemental analysis via optical spectroscopy. But then we have the Bunsen and Kirchhoff, who invented an luminous flame to study emission, show that alkali elements in the flame remove lines from a continuous source. Then Walsh noticed that molecular spectra are often obtained in absorption, but atomic spectra are always obtained in emission. And proposes to use atomic absorption for elemental analysis. So advantages over emission: far less interference, avoid problem with flame temperature. So atomic absorption spectroscopy, you can be able to see the sample is atomized, as we had already explained. UV-visible light is projected through the flame, then the atoms absorb light, reducing the beam. Then the difference in intensity is measured by the spectrometer. So you can be able to see the source of light there, the holocathode lamps. Holocathode lamps. And then we have a Keller. We still have it here, Keller gratings. Then we have sample nebulizers, where it produces aerosol of samples to introduce into the flame. Then we have detectors, still CCD, and PMT. The monochromator remove emission from the flame. Then modulated source, what we call the chopper, for a case where we have to separate the beam into two equal beams. Also remove the remaining emission from the flame. The signal of interest is given an AC modulation and passed through a high pass filter. Spectral interference, other flame components, particulates, etc. Scattering can cause similar problems, and this can be helped by background correction. So you can see graphite furnace and electrothermal atomic absorption spectroscopy. We have the hydride generation atomic absorption spectroscopy, and then we also have the mercury cold vapor atomic absorption spectroscopy. And the detection limits of atomic absorption spectroscopy, as you can be able to see. So in comparison, the flame, the electrothermal, and the ICP-OES, you can see the variation there. So detection limit in parts per billion. For selection of elements, individual results can vary depending on system. And so for atomic absorption and ICP-OES, samples are dissolved or digested into solution, flowed into the flame, plasma, and analyzed. Two methods for quantitative analysis calibration. We have the standard calibration and we have the standard addition. Special analysis may be needed. At the end, the results yield elements in parts per million, parts per billion, milligram per milliliter, or below limit of quantitation or limit of detection. And atomic fluorescence was developed as an alternative to atomic absorption and inductively coupled plasma optical emission spectroscopy with potential greater sensitivity. Has not yet achieved widespread use, but cheaper tunable lasers may change this. So the lasers stimulated emission, coherent emission from an excited state induced by a second photon. So you can be able to see processes that emit photon. Majorly the non-radiative processes and the thermal processes. Atomic fluorescence, you can see the radiation is at right angle to the sample. That's very important to note. And that's the major difference between AAS and atomic fluorescence. So in comparison now, plasma emission, atomic absorption, and atomic fluorescence, dynamic range is wide for ICP-OES. For AAS limited. For fluorescence is also wide. You know what dynamic range is. Then we have qualitative analysis is good, but it is very poor in atomic absorption, and also fluorescence is very poor. Then multi-element scan for plasma is good, but both AAS and atomic fluorescence are poor. Trace analysis for plasma, it's very good. Atomic for all of them, they are good. Small samples, all of them are good. Matrix interference is low. In in ICP-OES. Is low in ICP-OES, and so small samples are good. So matrix interference, we see that It is low in ICP-OES. They are very high in AAS and low in atomic fluorescence. Then spectral interferences, high in ICP-OES, but very low in AAS and low in atomic fluorescence. Cost, plasma emission is moderate. AAS is low. Atomic fluorescence also moderate. So this can really help you to choose which method to use in the analysis. Thank you.